Heat, it's all around us. From the moment the sun rises in the morning to when it sets in the evening, heat is a constant presence in our lives. It's in the warmth of the sun's rays, the heat radiating from a hot pavement, and even in the cozy warmth of a campfire. But heat is more than just a feeling, it's a form of energy that is essential to life as we know it. We can feel it, we can see its effects, and it plays a crucial role in our everyday lives. Heat affects everything from the weather patterns we experience to the way our bodies function. On a hot day we might seek shade or a cool drink to escape the heat, while in colder weather, we rely on heating systems to keep us warm. Have you ever wondered how heat actually moves from one place to another? What is heat anyway? Heat transfer is a fascinating process that occurs in three main ways: conduction, convection, and radiation. Each of these methods plays a unique role in the way heat is distributed in our environment. Understanding these processes can help us better manage heat in various applications, from cooking food to designing energy-efficient buildings. In the world of industry, understanding heat transfer is critical. Factories and industrial plants rely on precise control of heat to ensure their machinery operates efficiently and safely. For example, in a power plant, heat generated from burning fuel must be carefully managed to produce electricity without causing damage to the equipment. Engineers and scientists work tirelessly to develop new technologies and methods to improve heat transfer and reduce energy consumption. It's the key to designing efficient systems, preventing equipment failure, and even keeping people safe. Proper heat management can prevent overheating, which can lead to equipment breakdowns or even dangerous situations. In addition, efficient heat transfer can help reduce energy costs and minimize the environmental impact of industrial processes. By understanding the principles of heat transfer, engineers can create more sustainable and reliable systems. From the smallest microchip to the largest power plant, heat transfer is a fundamental process that can't be ignored. In electronics, for instance, managing heat is crucial to ensure that devices function properly and have a long lifespan. Overheating can cause electronic components to fail, leading to costly repairs or replacements. On a larger scale, power plants must efficiently transfer heat to generate electricity and provide power to millions of homes and businesses. In this journey through the world of heat transfer, we'll explore the three main ways heat travels: conduction, convection, and radiation. Conduction occurs when heat is transferred through direct contact between materials, like hot steel slabs on a factory conveyor. Convection is the process of heat transfer through the movement of fluids, such as air or water. This phenomenon plays a crucial role in natural and industrial processes, driving ocean currents, influencing weather patterns, and transferring heat in systems like steam boilers, where heat moves from the heating surface to the fluid through convection. Radiation, on the other hand, is the transfer of heat through electromagnetic waves like the warmth we feel from the sun. We'll see how these principles apply to real-world industrial situations, understand why heat dissipation is so important, and discover how the latest technologies are helping us manage heat more effectively than ever before. Innovations in material science, for example, are leading to the development of better heat-resistant materials and more efficient cooling systems. Solar panels, which convert sunlight into electricity, are another example of how we can harness and manage heat for sustainable energy solutions. Get ready to get fired up about heat transfer. Whether you're an engineer, a scientist, or just someone curious about the world around you, understanding heat transfer can open up a whole new perspective on how we interact with and harness the energy that surrounds us every day. So, let's dive in and explore the incredible world of heat transfer together. Let's start with conduction, the most direct form of heat transfer. Conduction occurs when heat energy travels through a solid material. Think of a frying pan on a stove. The burner heats the pan directly, and that heat is then conducted through the metal to your food. This is a simple yet powerful example of conduction in action. In industrial settings, conduction is everywhere. It's a fundamental process that plays a crucial role in the operation of countless machines and systems. One example is in bearings, those essential components found in countless machines. Bearings are designed to reduce friction between moving parts, but if a bearing is misaligned, it creates friction. This friction generates heat, which is conducted through the bearing material. Over time, this can cause the bearing to overheat and fail, leading to costly downtime. The heat generated by friction can be significant, and if not properly managed, it can lead to serious damage. This is why regular maintenance and proper alignment of bearings are so important in industrial settings. But conduction isn't just limited to bearings, it occurs in many other parts of industrial machinery as well. For example, heat exchangers rely on conduction to transfer heat from one fluid to another. This process is essential for maintaining the proper temperature of various systems and ensuring efficient operation. Another example is in the metal structures of buildings and bridges. These structures can absorb heat from the sun and conduct it throughout the material, affecting the overall temperature and stability of the structure. Understanding how conduction works and how to manage it is crucial for engineers and technicians working in these fields. In summary, conduction is a fundamental process that plays a vital role in both everyday life and industrial applications. From cooking food to maintaining machinery, understanding how heat is transferred through solids can help us better manage and optimize these processes. So next time you feel the heat, remember the role of conduction in making it all happen. It's a powerful force that shapes our world in more ways than we might realize. And with that, we've only scratched the surface of the fascinating world of heat transfer. Stay tuned as we explore more about how heat moves and affects everything around us. From conduction to convection and radiation, the journey of heat is truly remarkable, and it's a journey that impacts our daily lives in countless ways. Next up is convection, where heat energy travels through fluids like liquids and gases. This process is fundamental in many natural and man-made systems. Convection occurs when a fluid, such as water or air, is heated, causing it to expand and become less dense. This less dense fluid then rises while cooler, denser fluid sinks to take its place. This creates a continuous circulation pattern that transfers heat throughout the fluid. Imagine a pot of water boiling on a campfire. As the water at the bottom of the pot heats up, it becomes less dense and rises to the surface. This movement of hot water to the top and cooler water to the bottom creates a convection current. You can see this in action as the water bubbles and circulates. The burner heats the water at the bottom, causing it to become less dense and rise. This rising hot water then transfers heat to the cooler water at the top, which in turn sinks to the bottom to be heated. This cycle continues, creating a dynamic and efficient way to distribute heat throughout the pot. Cooler water then flows in to replace it, creating a continuous circulation of heat. This process not only ensures that the water heats evenly, but also prevents hot spots from forming, which could lead to boiling over or uneven cooking. Convection is essential for cooling many industrial systems. In large-scale operations, such as power plants or manufacturing facilities, managing heat is crucial to maintaining efficiency and safety. Cooling towers, for example, rely on convection to dissipate heat from the water used in various processes. Take motor housings, for example. Electric motors generate a significant amount of heat during operation. If this heat isn't effectively removed, it can lead to overheating and potential damage to the motor's components. Motors generate heat during operation, and if this heat isn't removed, it can damage the motor windings. Overheating can cause insulation to break down, leading to short circuits and motor failure. This is why efficient cooling is so important. That's where convection comes in. By designing motor housings with features that enhance airflow, such as fins or vents, manufacturers can ensure that heat is effectively dissipated. This helps maintain optimal operating temperatures and prolongs the life of the motor. Many motor housings are designed with fins that increase their surface area. These fins help to dissipate heat more efficiently by increasing the contact area with the surrounding air. As the motor operates, the fins facilitate the transfer of heat away from the motor and into the air. As hot air rises from the motor, cooler air is drawn in, creating a convection current that helps keep the motor cool. This natural process of heat transfer is a simple yet effective way to manage temperatures and ensure the reliable operation of various systems. Heat transfer occurs in three fundamental ways: conduction, convection, and radiation. While conduction requires direct contact and convection relies on fluid movement, radiation is unique. It transfers heat without any physical medium. But how does radiation heat transfer impact equipment, and why is it critical to understand? Radiation heat transfer occurs when energy is emitted in the form of electromagnetic waves, primarily infrared radiation. Unlike conduction and convection, radiation doesn't need air, water, or any other medium to transfer heat. It can occur even in a vacuum. The sun warming the earth, the glow of molten metal, and the heat radiating from an engine block are all examples of this process in action. That's radiant heat, traveling millions of miles through space. Radiative heat transfer plays a vital role in various equipment and industrial processes. In furnaces and kilns, radiation is the primary method of heat transfer, allowing for uniform heating of materials. In power plants and automotive engines, managing radiated heat is crucial for efficiency and longevity. Properly managing radiation heat transfer can mean the difference between optimal performance and catastrophic failure. Uncontrolled heat radiation can cause overheating, material degradation, and increased energy waste. Engineers and maintenance professionals use specialized coatings, reflective surfaces, and thermal insulation to regulate radiation, improving efficiency and reducing heat loss. In industry, radiation is often a concern in electrical cabinets. Electrical components generate heat, and if this heat builds up within an enclosed cabinet, it can damage sensitive equipment. Thermal cameras can be used to identify hotspots in electrical cabinets, allowing technicians to address potential problems before they lead to equipment failure. From aerospace applications, where spacecraft rely on radiation heat transfer to balance temperatures, to high-efficiency industrial heat exchangers, understanding and optimizing thermal radiation is a game changer. Advances in infrared imaging and radiative heat barriers continue to improve how industries manage heat, leading to smarter, more efficient designs. Excess heat buildup in equipment isn't just an inconvenience, it's a threat to performance, efficiency, and lifespan. Overheating can lead to component failures, unplanned downtime, and even safety hazards. So, how can we effectively release excess heat and maintain optimal operating conditions? We've learned about the 3 ways heat travels, but just as important is understanding how to manage it. That's where heat dissipation comes in. Heat dissipation is all about removing excess heat from a system, preventing it from overheating and causing damage. Think about your computer. It generates a significant amount of heat, especially the processor. That's why computers have heat sinks, those metal devices with fins, and fans to dissipate the heat. The first line of defense against heat buildup is passive cooling, using design features to naturally dissipate heat without requiring additional energy. This includes heat sinks, metallic components that absorb and disperse heat efficiently. Thermal coatings, specialized materials that reflect or absorb heat to regulate temperature. Ventilation, designing enclosures with proper airflow paths to encourage natural heat dissipation. When passive cooling isn't enough, active cooling systems come into play. These systems actively remove heat using mechanical or fluid-based solutions. These may include implementing forced air cooling, using fans and blowers to circulate air and remove trapped heat. Liquid cooling, pumping coolant through heat exchangers to absorb and transfer heat away from critical components. Phase change cooling, leveraging refrigerants or heat pipes to move heat more efficiently. Beyond cooling systems, environmental factors play a crucial role in heat dissipation. To maintain efficiency, consider proper placement, keeping equipment away from confined spaces or direct heat sources. Implement regular cleaning on equipment using cleaning and inspection standards. Dust and debris buildup can block airflow and insulate heat-sensitive components, causing the equipment to be under excessive heat buildup and premature failure. Implementing conditional monitoring techniques, infrared thermography, using sensors and thermal imaging to detect hotspots before they become critical. With advancements in technology, industries are adopting smarter heat dissipation solutions. One such advancement is AI-driven cooling, systems that adjust fan speeds and coolant flow based on real-time data. Another advancement is waste heat recovery, repurposing excess heat for other processes to improve energy efficiency. Excess heat buildup is one of the biggest challenges in equipment reliability. Whether through passive cooling, active systems, or smart heat management strategies, efficient heat dissipation is key to performance, safety, and longevity. Thermal imaging is a powerful tool for identifying potential issues in equipment before they lead to costly failures. But what should you look for? And how do different heat signatures reveal critical insights? Thermal imaging works by detecting infrared radiation emitted by objects, translating temperature differences into a visible heat map. The hotter an area appears, the more energy it emits. But not all heat is a problem, so how do we determine what requires attention? We can use tools like thermal imaging cameras to visualize heat patterns. These cameras don't see light like we do. They see temperature differences, represented by different colors. For example, a thermal image of a machine might reveal a hot spot on a bearing, indicating potential misalignment. This allows technicians to address the issue before it leads to failure. When scanning equipment with a thermal imaging camera, Look for abnormal signatures such as hotspots. Unusual hotspots refer to localized areas of excessive heat that deviate from normal operating temperatures. For example, electric motors are designed to function within a specific temperature range. If this range is exceeded, it can degrade internal windings, leading to premature failure. On a thermal image, this will appear as intense high heat spots concentrated in critical areas. To assess the severity, compare the detected temperature against manufacturer specifications. Identifying and addressing these anomalies early can prevent costly breakdowns and extend equipment life. Another important heat signature to watch for is asymmetry. Temperature differences between identical components operating under the same conditions. For example, when performing thermal imaging on bearings to check for misalignment or wear, all bearings within the same assembly should exhibit similar temperature profiles under the same load. If one bearing appears significantly hotter or shows a localized heat spot at the bottom, it could indicate a developing issue such as spalling, pitting, or lubrication failure. Detecting these irregularities early allows for preventive maintenance, reducing the risk of costly breakdowns and extending equipment lifespan. Heat concentration around electrical connections often indicates loose connections, overloading or failing components, leading to excessive resistance and localized heating. These thermal patterns can also reveal high-resistance faults, damaged wiring carrying unintended current, and imbalanced loads, all of which may pose serious fire and safety risks. Detecting these issues early through thermal imaging allows for preventive maintenance, reducing the likelihood of failures, energy waste, and hazardous conditions. Heat map signatures provide a visual representation of failure modes in components under evaluation, revealing critical issues before they escalate. Hotspot clusters, localized overheating in bearings, motors, or mechanical systems often indicates excessive friction, which can result from misalignment, inadequate lubrication, or early-stage component degradation. If left unaddressed, these heat concentrations may lead to accelerated wear, reduced efficiency, and potential failure. Irregular heat in electrical panels, excessive heat in breakers, fuses, or wiring connections is a strong indicator of electrical resistance, often caused by loose connections, corrosion, or circuit overloading. These heat anomalies can lead to voltage drops, energy loss, and potential fire hazards if not addressed. Regular thermal inspections help identify these issues early, allowing for preventive maintenance to enhance electrical system reliability and safety. Uneven heating in pipes or ducts. Erratic temperature patterns in pipes or ducts often signal underlying issues such as blockages, insulation failures, or restricted fluid flow. These irregularities can lead to inefficiencies in heat transfer, increased energy consumption, and potential system strain. By using thermal imaging, operators can pinpoint these anomalies early, ensuring optimal performance, preventing heat loss, and avoiding costly repairs. Gradual heat buildup in rotating equipment. A steady increase in temperature over time in motors, gearboxes, or rotating machinery often indicates worn bearings, unbalanced components, or insufficient cooling. This progressive overheating can lead to increased friction, thermal expansion, and eventual component failure. Regular thermal monitoring allows for early detection, enabling proactive maintenance to prevent costly downtime and extend equipment lifespan. Thermal imaging isn't just about spotting hotspots, it's about predicting failures before they happen. By understanding heat signatures and taking proactive steps, you can enhance equipment reliability, reduce downtime, and improve operational efficiency. Once a hotspot is detected, the next step is to identify its root cause. The first step in this process is to compare historical thermal scans to detect developing trends, provided that previous scans exist. By analyzing past data, maintenance teams can determine whether the heat anomaly is part of a gradual trend, indicating wear or inefficiency, or if it is a sudden spike, signaling an imminent failure. This historical comparison allows for data-driven decision-making, helping to prioritize corrective actions and prevent unexpected breakdowns. By analyzing thermal imaging data over time, patterns of gradual heat buildup, emerging hotspots, or abnormal temperature fluctuations can be detected before they lead to equipment failure. Trending thermal data helps identify progressive wear, misalignment, electrical resistance, or cooling inefficiencies, allowing maintenance teams to predict failures, schedule proactive repairs, and optimize system performance. After reviewing trends for the component in question, it is crucial to cross-check findings using complementary diagnostic methods. Vibration analysis, ultrasound testing, and visual inspections provide additional insights to confirm whether the anomaly is caused by mechanical wear, misalignment, electrical faults, or insufficient lubrication. Thermal imaging serves as the first line of detection, pinpointing potential failures and their exact locations by identifying abnormal heat patterns. However, to fully understand the root cause, cross-checking with vibration analysis is essential. Vibration analysis provides supporting details by detecting mechanical issues such as bearing wear, imbalance, or misalignment, which may be contributing to overheating. By correlating thermal imaging with vibration data, maintenance teams can distinguish between electrical and mechanical failures, ensuring precise diagnostics and effective corrective actions. This multi-technique approach enhances predictive maintenance strategies, reducing unexpected failures, and extending equipment lifespan. Ultrasound testing is a powerful diagnostic tool that detects subtle, high-frequency sounds beyond human hearing, making it an essential complement to thermal imaging and vibration analysis. Ultrasound testing identifies compressed air, gas, or vacuum leaks, which can lead to energy losses and inefficiencies. Detects corona, arcing, and tracking in electrical systems, preventing insulation failures and potential fire hazards. Pinpoints incipient bearing wear, inadequate lubrication, or mechanical rubbing, which may not yet show as significant heat buildup, but will eventually lead to overheating and failure. By integrating ultrasound testing with thermal imaging and vibration analysis, maintenance teams gain a comprehensive view of equipment health, enabling early intervention and targeted maintenance actions before minor issues become critical failures. Visual inspection remains a fundamental yet often overlooked step in identifying potential failures. While thermal imaging, vibration analysis, and ultrasound testing provide advanced diagnostics, a direct visual assessment can reveal critical issues that technology alone might not detect. Visual inspection reveals loose connections, identifies improperly secured electrical or mechanical components that can lead to overheating, vibration, or failure. Visual inspections uncover contamination, detects dust, debris, moisture, or chemical buildup that may be insulating heat or accelerating component degradation. Physical damage such as cracks, corrosion, worn insulation, or other mechanical stress indicators that contribute to equipment inefficiencies are revealed during visual inspection of components and parts. Visual inspection reveals external heat sources, identifies surrounding equipment, poor ventilation, or environmental factors that may cause false thermal readings or unintended heat buildup. By integrating visual inspection with predictive technologies, maintenance teams can validate diagnostic findings, eliminate false positives, and take corrective action with greater confidence, ensuring optimal equipment performance and reliability. By integrating multiple diagnostic tools, maintenance teams can validate thermal imaging results, ensure accurate root cause identification, and implement targeted corrective actions before failures occur. Prioritize repairs based on severity. Critical overheating demands immediate attention, while moderate heat deviations warrant monitoring. Schedule preventive maintenance to address root causes before failure occurs. Section 8. The future of heat management. As technology advances, so too do our methods of heat management. Nanomaterials with exceptional heat dissipating properties are being developed. Advanced cooling systems like liquid cooling and heat pipes are becoming more efficient and compact. With the onset of the digital transformation age via smart factory, AI becomes the next advancement in compare historical thermal scans to identify developing trends. By analyzing historical thermal imaging data, AI-driven systems can detect subtle temperature variations, progressive heat buildup, and emerging hotspots long before they escalate into critical failures. Unlike traditional manual analysis, AI continuously monitors trends, identifying anomalies that may indicate wear, misalignment, electrical resistance, or cooling inefficiencies. With machine learning algorithms, AI can recognize failure patterns by comparing real-time scans to historical data, predict potential breakdowns before they cause downtime, optimize maintenance schedules by prioritizing components at risk, reduce false alarms by distinguishing between normal fluctuations and critical deviations. By integrating AI-driven predictive maintenance, companies can eliminate guesswork, reduce maintenance costs, and extend equipment lifespan, ensuring peak performance with real-time data-driven decisions. The future of heat management is exciting, with innovations constantly emerging to address the challenges posed by ever-increasing heat loads in electronic devices and industrial equipment. Thermal imaging is a non-destructive technique that transforms basic maintenance into a preventative strategy, enhancing equipment longevity. Heat transfer is an integral part of our world, especially in industry. By understanding the principles of conduction, convection, and radiation, and by recognizing the importance of heat dissipation, we can design more efficient, reliable, and safe systems. As technology continues to advance, our ability to manage heat effectively will become even more crucial, ensuring that our machines and systems continue to operate at their best. So, next time you feel the heat, take a moment to appreciate the fascinating science behind it. Thank you for joining us. If you liked this video, please like, share, and subscribe for more.